things that our lab is interested in a lot is water quality, and on trying to figure out how, when chemicals are released to the environment, they're going to move, where they're going to concentrate, and how they'll break down. And in particular, we're interested in the rates of breakdown of things like oil and crude oil. And so the sediments that we have collected right now are from a wetland just west of Bemidji that was impacted by a crude oil pipeline. The crude oil comes from the Alberta tar sands in Canada. It takes roughly 10 to 15% of the entire nation's oil supply comes from Alberta, Canada, by way of this pipeline. And so the oil has been breaking down for more than 30 years. And one of the things that's really interesting is even after 2 remediation strategies, the oil is still there, and it's very sort of fresh smelling, if you will. And one of the things that we want to know is if there are things that that impact the rate at which it breaks down, or things that make that oil move faster. So maybe it's kind of localized in one area, but if you add something like, for example, ethanol, which we often store near gasoline, right, in many gas stations around the Twin Cities area, for example. If those 2 compounds are released simultaneously, what can happen is the ethanol can make the oil travel farther, is the hypothesis. And so one of the things that we're trying to evaluate is how much farther, and in particular, if you're moving through a wetland, which already has a lot of natural organic matter, how that material will break down. I think we just we're going to. So, for example, this is a water sediment slurry that is from the top of the wetland, and you can see it's a lot darker. So you have a lot more organic matter, naturally occurring organic matter. Where deeper as you go deeper within the wetland, the material becomes, you can see, much sandier, a lot less of that real dark organic matter. And so the oil is going to both move and break down really differently. We have a series of we've done some field testing, some field experiments, and now these are some companion laboratory experiments where we're adding a very specific chemistry to the water, and then we're able to connect these jars to an instrument called a respirometer. So St. Thomas, we have an instrument that measures continuously the breadth of the microbial community, if you will. So just like you eat your, you had a turkey sandwich for lunch and you take that carbon in and you're breathing out CO2. Well, there are literally billions of bacteria in this jar, and so the whole community itself is taking in the organic matter, the natural organic matter, the oil. If we add ethanol, then the ethanol. And then they're breathing things other than, there's not any oxygen in this system. We keep everything anaerobic. And they're breathing in things like nitrate or sulfate or iron, or simply just doing a process called methanogenesis. And so when those processes happen, they're breathing out CO2 and they're breathing out methane. And so our analyzer analyzes the breadth, if you will, of the microbial community. And we can look at changes in the amount of carbon dioxide that comes out and the amount of methane that comes out. And from that we can infer how much carbon has been transferred into those gases. And wetlands themselves actually produce quite a bit of methane into the atmosphere, which is of course also a greenhouse gas. So we get a sense of how much methane is being produced by these systems, and of course CO2 is also a greenhouse gas. What is the carbon cycling in these systems like, both naturally and contaminated, because our controls would not have the oil added to them.